Okay, so in this video we're going to take a look at a different problem. In this one I have set up a scenario in which I've sent a message in a bottle out to sea. Now the bottle is a type of mason jar. We're going to treat it as a cylinder, and I've got a message inside of it, something like this. Not enough room for more exclamation points, but that's okay. Now, I know that the dimensions that I have on this bottle are going to be 8 centimeter diameter, and it's got a height of 12 centimeters. Okay, I put this out in the water, and the mass of this jar and message comes up to 500 grams, which is 0.5 kilograms. I want to know how easy it'll be to see this particular jar, and so I'd like to know how high above the water level the top of the jar is going to be. And this one can be a little bit trickier. What we're going to do here is a little bit more than what you may be familiar with. Up to this point we talked about whether or not something would float by comparing its density of object, versus the density of water, if we wanted it to float in water. If the density is less than that of water, then it would float. But there's more that we can do than simply tell whether or not something's going to float. We can actually predict this height, h. Okay, well, the way we're going to do that is by actually looking at the forces involved. Now, the big thing that we'll need to know is the force of buoyancy. Now, the force of buoyancy is basically equal to the weight of whatever the fluid that is displaced. So in this case, we're going to deal with the mg of the water that we have displaced by putting this jar into it. Okay? Well, how are we going to find the mass of water that's displaced? Well, we know that mass is going to be the same thing as volume times density. So if we can find the volume displaced, we know the density, and we know the acceleration due to gravity, then we can find out the mass of water that we've displaced. Okay, well, what we're going to do is we're going to draw a free body diagram of our jar, and we've got its weight, mass of the jar, times gravity, like usual, force of gravity trying to pull it down. In this case it's going to float, so we know that there's a force holding it up. Well, in this case it's the force of buoyancy. And if I apply Newton's second law, I'm going to have my sum of forces. We're going to look in the y direction. That's going to be our force of buoyancy minus mass of the jar times the acceleration due to gravity equals our mass times our acceleration in the y. Well, this guy's just going to float there, so ideally he might bob up and down a little bit from fluctuations, maybe some waves, but we're looking for the area where it just kind of floats there, and it's nice equilibrium position. So we're going to assume that that equals 0. We can add our mass of the jar times gravity to both sides, times gravitational acceleration, I should say. And we find that our force of buoyancy equals our mass of the jar times the acceleration due to gravity. Okay, well, we know the mass of the jar, that's 0.5 kilograms. We know the acceleration due to gravity, 9.81 meters per second squared. And our force of buoyancy is nothing more than, we've got marked here, it's the mass of water displaced multiplied by g, and we can replace that with our volume displaced, so how much space is taken up beneath the water by our jar, times the density of water times the acceleration due to gravity equals our mass of the jar times acceleration due to gravity. We can see that in this case g actually falls out, which is good. And if I solve for my volume, I'll find that it's the mass of the jar divided by the density of water. Okay, and the volume, well, we're dealing with a cylinder, so we're going to deal with the volume of a cylinder, which equals our height times pi r squared, where r is going to be equal to 4 centimeters, which is equal to 0.04 meters. Our h, well, if we were finding the volume of the entire cylinder, then it would be 12 centimeters tall. But we're finding the volume of the water displaced, so the cylinder is only going to be as tall as from the bottom of our message here to the water level. Well, actually, if we can find that, that's this here. If we can find this, then we can find what we're actually looking for, our height above the waves. Okay, so I'm going to replace that. I've got h times pi r squared, which is going to be 0.04, sorry about that, meters, and we'll square that quantity. It'll be equal to mass of the jar, which is 0.5 kilograms, divided by density of water, which is 1,000 kilogram per cubic meter cubed. I know pi, I know 0.4 meters, and I can square that. I know everything on this side, so that just leaves my h, and when I solve for that height, I find that it comes up to 0.0994 meters. In other words, my height comes up to right at about 10 centimeters. Okay, well, if this is 10 centimeters, then the amount that's above the waves equals approximately 2 centimeters. That's how much can be seen above the waves. Now, you'll notice that what we've learned from this is not only that we can check to see whether or not the message will float, but we can actually use the exact values to find out how much of it will be above the surface of the water. And this is the sort of thing that can be pretty useful in a lot of different situations. So knowing the force of buoyancy allows us to be able to find out how much water needs to be displaced and how well something's going to float, how high above the waves it may be. In fact, if you go online and you look for how heavy different ships are, like maybe an aircraft carrier, or a submarine, they'll actually give you the weights in displacements. They'll tell you that it displaces X amount of tons or X tons of water. That's its displacement. What it's actually telling you is how heavy it is, because it tells you how much seawater it's displacing. And we know by our relationship here that the buoyant force, how much it displaces, is directly related to its weight.